Welcome to this presentation on the problem of checking if a parenthesis string can be valid. In this session, we will explore the problem statement, break down valid parentheses, go through examples, and explain the solution approach in detail. Let's start with the problem statement. We are given two strings S, which is a parenthesis string consisting of parentheses, and locked, a binary string of ones and zeros. The string S can only be modified where the corresponding value in locked is 0. Our goal is to determine if we can make S a valid parenthesis string by modifying it under these conditions. So what exactly is a valid parenthesis string? A valid parenthesis string satisfies three conditions. First, it is an empty pair. Second, it can be written as AB, where A and B are valid parenthesis strings. Finally, it can be written as parenthesis and A, where A itself is a valid parenthesis string. Let's look at some valid parenthesis string examples. This includes the string containing two parentheses and so on. Each of these examples follows the rules we have just mentioned. Notice how the parentheses are properly paired and nested. Now let's look at some invalid examples. This includes the following. In these strings, the parentheses are not correctly paired or nested, which makes them invalid. Here we have example 1. The string S is given like this and log string is 010100. We can modify the characters where log tie is 0. So we can change S0 and S4 to the opening while leaving S2 and S5 unchanged, resulting in a valid parenthesis string like this. After modification, the string becomes this, which is a valid. Notice how we transform the string to meet the required conditions for valid parentheses. In example 2, the string S is already valid. The string is balanced and the log string is 0000, allowing us to make no changes. Thus the output is true because the string is already a valid parenthesis string. Let's look at example 3. Here the string S is the closing parenthesis with a log string of 0. Although we can change the character, there is no way to form a valid parenthesis string from this. No matter whether we change the character to a opening parenthesis or a closing parenthesis, the string will remain invalid. Thus the output is false. The problem provides some constraints. The length of the string is between 1 and 1 lakh. Each character in S is either a opening parenthesis or a closing parenthesis, and each character in log is either 0 or 1. These constraints guide the design of our solution. To solve this problem, we use a two-pass approach. First, we perform a left-to-right pass to maintain balance while considering locked and free positions. Second, we perform a right-to-left pass to ensure the balance remains valid across the entire string. In the left-to-right pass, we maintain a balance of open and closed parentheses. We also keep track of free positions where log tie equals 0. During this pass, if the balance plus the number of free positions becomes negative, we immediately return false. Here is the code for the left to right pass. As we iterate through the string, we adjust the balance based on the logged string and the current character. If at any point the balance plus the free positions becomes negative, we return false, indicating an invalid string. The right to left pass ensures that the parenthesis string remains balanced in the opposite direction. By checking from the end of the string to the beginning, we make sure there are no unmatched opening parentheses. This is the code for the right to left pass. Similar to the left to right pass, we adjust the balance and track free positions. If the balance plus the free positions becomes negative, we return false, indicating the string cannot be balanced. Here is the code. The time complexity of the solution is big O of n as we traverse the string twice. The space complexity is big O of 1 since we use only a few variables to keep track of the balance and free positions. In conclusion, we have a solution that efficiently checks if a parenthesis string can be valid. By using two linear passes over the string and tracking balance and free positions, we can determine the validity in optimal time and space. Thank you for your attention. If you have any questions or would like further clarification, feel free to ask. I am happy to help.